Hey everybody, and welcome back to I Hate Chemical Engineering. This is the fourth video in our THERMO 1 series, where we're going through Smith and Van Ness and Abbott's text, Introduction to Chemical Engineering Thermodynamics. Again, this course is going to be applicable to anyone who wants to learn about thermodynamics across the various disciplines. But in particular, it's kind of made for chemical engineers. And we're going to do examples as we move through the book from the back of each chapter. And I understand that you're probably hankering for an example by now. We've had 3 lessons or 3 videos where we finally got to the energy balance equation. But just knowing the energy balance equation really doesn't do a lot in terms of giving you valuable examples, real-world examples. And that's because we've yet to talk about something that's really important and common, I guess, and commonly learned, even before the thermodynamics course. And that topic is heat capacity. Now, heat capacity is something that you've probably learned, like I said, in general physics before the thermo course. But there are some nuances, at least from a thermodynamics perspective, that need to be elaborated on. And in order to do so, we need to talk first about compression and expansion work. Now, compression and expansion work is the last form of work that we've neglected at this point to talk about. So, if we talk about all the forms of work, we've looked at flow work, right? At this point, which went into the definition of enthalpy. And we've talked about shaft work, right? Which, again, you can think of that in terms of like useful turning of a shaft, right? To transfer energy into or out of the system. We didn't really describe in a lot of ways on what that actually looks like. We talked about an agitator, a stirrer, you could say, putting energy into the system. Pumps would do the same thing, but also like a turbine, would take energy out of the system, like in a hydroelectric dam, let's say, where, the system is, the water's turning a turbine or generator, right, to produce electricity. Now, the last form of work is compression and expansion work. And that's what we're going to discuss today. And you'll see in the next lesson on why we're going to choose to talk about it now. It's not a very complex topic, and it's a little premature to talk about it in terms of when you're going to use it. But it is because it's lack of complexity, I don't mind talking about it now. So let's just jump right in it. So let's draw for us a system here. Let's have a. Whoa, that is not the shape I was going for here, fellers. Let's draw us a cylinder. So we got a cylinder, that's got a piston in it, just like an engine. And that cylinder is going to experience a change. So right now we've got a piston at state 1. Let's say this is the initial state. And it moves into state 2. And we don't know how or why it moves from state 1 to state 2. And this piston has an area across its face, or the cylinder, excuse me. And it sits at a current length from the back end of the cylinder, equivalent to X. And moving from state 1 to state 2, we get a change, delta X. So the gas in this piston, so we'll say there's gas here, that's exerting a pressure across the piston face, And we don't know what that pressure is, and we don't know if the pressure is identical or changes between state 1 or state 2, but suffice it to say, there's a pressure that's across that piston, or pushing against that piston. So what does this have to do with work? Well, what we know is that work is going to be equal to, from general physics, right? Differential work added to the control volume is going to be equal to negative force times distance. And we say negative here, and I wanted to note that this is important here, because we're talking about in reference to the control volume, right? So, in other words, if the distance that the piston moves is positive, so in other words, moving from state 1 to state 2, that distance x grows, so it gets bigger. The work done by the control volume is going to be negative. In other words, energy is leaving the system in order for the control volume to get bigger, right? So, but again, that's kind of a small but very important point that I need you to remember. So, but again, the differential work is going to be equal to force, the negative force times a differential distance. So, what is the force? Well, we know that the force at every point x is going to be equal to the function that the pressure is at x times the area at point x. So whatever, at each individual point x, there will be a pressure and an area. And we don't know how, we're making no claims to understand exactly what the pressure is at each of those points. But what we do know is that the force at each of those points is going to be equal to the pressure at each of those points times the area at each of those points. In our scenario, area is a constant, right? So we'll just go ahead and say force equals pressure, or area times pressure of x there. So plugging that into the equation, we know that dW equals negative a p of x dx. So we have an interesting thing here, though. At this point, we have an a and a dx. So what is the volume of the control volume? Well, the volume of the control volume initially is going to be AX. So that's the volume. At any point in time, it's AX. Right? So what is the differential volume? Well, it happens to be the differential of the product, which is going to be A dx plus X dA. And again, we said A is a constant, so we end up with dV equals A dx, which just so happens to be what's in the work equation above. So in the end, plugging and chugging here, we get differential work added to the control volume is the negative pressure times the differential change in volume. Now, that's called compression and expansion work. Why? Because the work is done on the control volume as the gas, as a piston, or you could think of it as, any flexible control volume, in the sense where the total volume is not held constant. As that volume expands against, and pushes against its environment, that push does work against the environment. And when the environment collapses against the control volume, that environment does work against the control volume. So, taking that integral to its logical conclusion, we end up with work equals negative integral of the differential volume of P times the differential volume. Pressure times the differential volume. Now, again, we've made no claims as to what the pressure is as a function of volume. And that pressure in all reality can look very different across the many different ways that these what we call engines or engine cycles can work. So in certain situations, the pressure could be constant as the volume increases. Right. In other situations, the pressure is not. The pressure could even decrease as the volume increases or increase as the volume increases. So we're not making any claim one way or the other what that integral will turn out to look like. But that is the definition of expansion and compression work. And that will become more useful in the next 2 or 3 videos. All right, guys, thank you so much. And if you like that video, you can like, comment, and subscribe. After the next video on heat capacity, we will have examples to go through, and I think you will enjoy it. All right, appreciate you guys.